All right. So that's the give you some motivation why conformal mapping is important, right? Then the textbook has some example, just illustrate some of the property when you are doing the mapping, how to consider mapping, which part map to which. So there's some general idea, basically based on the fact that these functions are continuous. So the textbook use a simple, very simple, very, I mean, extremely simple example. So W is one of the Z. Try to just look at the mapping, right? So again, you have a Z plane mapped to a W plane, right? And the first the first consideration is just figure 11.33. So it's very simple. So obviously, the circle, unit circle of Z will map to a unit circle of W. Right? If Z is one here, so both X and Y are one, right? And this is a unit circle on Z. So magnitude of Z is one. Obviously, magnitude of W is still one, so you map to the unit circle of W. That kind of looks trivial. This is U and V, U and V. So this circle map to this circle. And but then when you look at specific point, that there's something different because specific points Z. In this case, Z on this circle, Z is e to the I theta. Right. This point will map to 1 over Z is what is it? E to the minus. So this point will map to here. So this is big. This will map to this one. This is W. Right. And obviously one will map to one, right? One will map to one. So this point map to this point, but this point actually map to the other point. So this, as you go from one to Z along theta, obviously this portion of the line will go the other direction. Right? So this is like reversing the order. One is counterclockwise, you map to a clockwise direction. So you can now figure out you start from one, increasing along this circle, or we start from one, going clockwise in this case. This working. So that help you to figure out how you map these different points. So this is one. Obviously, y equals 1 or I will map to 1 over I, which is minus I. So this point, so this if this is your point A, point B, let's say A point here. Your point B is I, then map to point B prime here. Right? Likewise, you can figure out other points. To use the concept of continuity will help you to find points on the corresponding mapping of what so A would be, B would be, the A prime, the relative position on the mapping. You can figure out by the continuity consideration. That. Another consideration is mapping the whole region, right? And obviously, the interior of the unicircle will map to another region. So the consideration is the boundary map to the unicircle. We know that. So that all the points in the interior will map to one region of the W plane. What do you think it is? What region on the W plane will this interior map to? Say that again. Outside the circle, right? And what is the consideration? Why is that so? Because it's one, yeah, the inverse of that. Yeah, you can, yeah, that is an obvious reason. Another reason is that there's a zero, z equals 0 point in the interior. Obviously, it's 1 over z singular at the infinity. That is what we call the singularity, the pole, right? this pole will map this to infinity. So this point will obviously map to infinity on the W plane. So by continuity, the region containing this point will be the region that contains infinity. So it must be mapped to this point. Right. You can use another situation. You use the concept of continuity that help you identify which part of the original domain will map to the whatever after you do the map to which part of the corresponding mapping. Okay, so that's one consideration. All right, the second figure in figure 11.34, the top figure. Let's look at that. Let's do here. All right. So that's the first curve is a little boring, right? Just a circle map to a circle. The other is still a circle map to a circle, but a little bit different. W plane. Let's look at what that part is. The W on the Z plane, you have 1 and 2, 3. So basically a circle, another circle, but this is not the center at the origin. So you have this circle center at 2. Wait, consider this is a point 1. This is a point A, which is 2 plus I. Point B is 2 minus I. Okay. Now you want to figure out the corresponding curve on the W plane. Right. Obviously, 1 will map to 1. We already know that. 1 obviously map up to 1. And actually, the scale is different. You want to map, choose 1 larger because everything is greater than 1 on the x-axis. So we need to do that a little bit larger scale on the W plane. The 1 map to 1, so we need this point. Now the other point, yeah, the 2, obviously 2 will map to, but this case will map to 1/2, right? 2 will map to 1/2. So 2 is the center of the circle. That will be 1/2, right? And then wherever this point 3 will map to 1/3, obviously. 1/3. So this obviously you see the scale is different, 1 to 2, and now map to this part, map to this part. So there seems to be a scale change, but and A is just, yes, considering just a specific example first. We can later on look at the functional form. So A is 2 plus I, right? And then it means that it will map to 1 over A. 1 over A is 2 plus I in the denominator, which is 4. 3, yeah, 3. No, 4, 5. 5 over 2 minus 1, right? 5 third over. So 5 third, 2/5. 2/5 is a little slightly less than 1/5, something like that. And 1/5 of I, minus 1/5 I. So A prime will be here. And obviously the corresponding point will be B prime. B will map to the other point. Because this is just complex conjugate, right? So we map to the complex conjugate of A prime. and that doesn't look like a circle, but your textbook drawing is a circle. Well, we can figure that out by looking at the general formula, right? So W is x plus I y, 1 over x plus I y, so it's x minus I y over x squared plus y squared. And so it means g is x squared plus y squared. V is minus y over plus y squared, something like that, right? Or the other way around, you can say the obviously you can invert that's transformation and express x as a function of u and v and y as a function of, and pretty sure you can convince yourself that the inverse relationship should be exactly the same form because they are symmetric. The W is 1 over Z, minus Z is 1 over W. So you solve X would be U V square plus V square. Y would be V, V square plus V square. Right? So this is if you want to write explicitly the transformation given by this explicit relation. Now, obviously, we have this specific point. You know the mapping. This curve will map to specific point on this. But to see what the curve, what the equation of the curve, you need to do a little bit of transformation. If this is originally a circle, it looks like a circle. Is the top is a circle? Look, looks like a circle. The circle of this is obviously is x minus 2 square plus y square equal to 1, right? Yeah. And then you can figure out the corresponding equation in u and v by this transformation. That means x is u, so u over e square plus v square minus 2 yeah, plus v square over v square plus v square. So this will go into that. Equals to, you can take the common, a square. Common denominator. Square, and then the numerator is, what is that? Small minus 2 square plus v square, and square plus v square. That looks complicated. What is that? That looks complicated. Because sometimes we work it out a little bit. V square, u square, and you have another v square, and then minus 2 u v square, v square, and then plus 4 of E square plus D square squared. Right. And the the E square that can cancel. One of the space so that let's continue up here. So it becomes cancel with one factor, become 1 minus 2u, right? E square, E square, and then plus 4.
Or doing that for you square plus b.
This one?
Yeah. No. That the last equation. The other one is also 4 because 2 times x square.
Ah, yeah, this is also true. This is also true. Good. Okay. So that equals to 1, right? Now you can multiply by v squared plus v squared, so 1 minus 4u plus 4. Or actually, you can combine the two first. Subtract that plus 3 v squared plus e squared. This is 0. Right? Now you're convinced that it looks like a circle. It looks like you can divide it by 3, so v squared plus v squared. This, right? And minus 4u over 3 and plus 1/3 0. You see, you get actually a circle or whatever quadratic curve. So what you do is do a complete square, u plus u over 3 plus u plus 3. Good. Right. U, right. Plus 1/3 minus 3/3 squared. That is u minus 3/3 square. I'm going to move those to the other side. 9, 4 minus 3, 4 minus 3. Did I get it correctly? So this is indeed a circle. The center, right?
V square.
Right. Oh, yeah, there's a v square. There's a v square. Yeah. V square. Right. That's the complete square of the u, but then. So this is a circle, and the radius is 1/3. Yeah. And then the center at 2/3, 1/3, 2/3. That is the center. And obviously she goes through this thing. But it's a circle. I didn't do it correctly. Right. So sometimes it's complicated, but you get the point. So it take a while to figure out the curve, how one curve will transform to the other curve. It might take a while to figure that out, but once you get all the transformation correctly and do some algebra, then finally, hopefully, you will get the answer. So that's the second figure, right? We had 10 people. Oh yeah, already overtime. So hopefully, I'll just finish the last topic, last example for the last topic, conformal mapping. I think we are just missing the last figure, the last part of the figure. Okay, so that is the figure 11.34. Where you map the circle to a straight line. So, last time we figured out the middle panel, the mapping a circle to another circle. As it turns out, this mapping has the property that any circle on one plane will map to another circle on the other plane, and that's kind of funny. But it would turn out for map, because last time we did it for the specific case, but you can generalize that to the general case and show that that's true. And then during the process, you can see that why you can sometimes map a circle to a straight line. So let's just go through it again. So I think, the mapping is W is 1 over Z, right? And last time we did that and solve for the transformation of real and imaginary part. You can now write Z is X plus IY, and let's solve this directly. Z is 1 over W, so it's 1 over U plus IV, which is U minus IV divided by U squared plus V squared, right? X is U over U squared plus V squared, Y is minus V over U squared plus V squared. Okay, that's the transformation. Now you consider a circle on the Z plane. Let's say, let's give it some names, X0, is 1 square, R square. So if there's a circle on the Z plane, say what will transform to, what shape is transformed to on the W plane. So you just substitute all this transformation. So it becomes U. Let's take the square. Let's take all the square out in this step. So just save one line. So X is U over U squared plus V squared. So X squared becomes U squared. V squared plus V squared square. Now you minus 2x0, x is U plus V square, right? And then minus x square. And do the same thing for the second term. That's V square plus V square square. And then minus 2y0. But there's a minus sign in here. So plus V square minus a plus y0 square term. I think this is also plus. Okay. This is square term. Y0 square. Okay. So can you follow this? Just direct substitution. Is that okay? Okay. Now you can group these two terms because they have common denominator. And the numerator becomes U squared plus V squared, so cancel one of the factor. So all four terms has U squared plus V squared, and the rest without that denominator. So you can find the common denominator, U squared plus V squared, and group all the terms, this plus that, and divided by the denominator, give you 1. And then this one has minus 2x U y v, and the rest is just, I mean, you can put the rest on the other side. Square minus now you can almost see that it's a circle, because if you multiply this to the other side, and we have V squared plus U squared plus V squared. So, and then you can do a complete square of that. Then that is, I mean, this can be positive or negative, but that turns out doesn't matter because after you do the complete square, you see that it still is a circle, right? Let's just multiply, group this, multiply this to the other side, and then combine with the other side to do the least square. I mean the complete square, right? So yes, let's just do it. Well, that may be a little difficult because you don't want the square term as 8, or you may divide this to the other side. So u square. So move it, divide this to the denominator, multiply this to the other side. We call it the u square plus v square. And so you have minus u x u divided by this. Right. I move to the other side. And then we have similarly for the v square. We can do the complete square of that first before we do the v square. Right? To complete the square, you need to plus x0 square over the square of that. Okay, and then you need to subtract that finally, but we can move that to the other side. Plus v square, and this time we minus minus. And do the same thing. Right? Square. And move this term, move this to the other, this to the other side. So you have the one term and move to the other side. Right? Minus, or let's write equals to minus 1 over. Right? And then subtract all these things. Subtract. Same thing for the square. Minus. This one?
No,
this one?
These the next one.
This one?
Yes, because it's the next. We are subtracting from.
Yeah. Plus, you're right. Okay. This part is just to show this positive because this should give you the radius. And do a common denominator, and the numerator here becomes, I mean, the square of this. The numerator of this is r square minus x0 square minus y0 square, but with a minus sign inside, become r square, become positive r square minus x0 square minus y0 square. But you combine with these two terms, so you cancel the x0 square and y0 square, because just r square. And then the denominator is the square of this. So that's the radius, square, the square of the radius on the W plane. And these two are just the, I mean, you can just write them easily. This is u minus u plus x0 minus x0 minus y0 v minus Let's see. Minus twice square. Yeah. Okay. Now the center of the circle is this two location. So U is minus of this one, V is this one, and the radius is the square root of this one. Is that okay? Hopefully, if I get everything correctly, is but at least you see that from this process, you see that it's a circle. So whatever circle on the C plane will transform to map to a circle on the W plane. And then this give you the formula how you transform the center from x0, y0 to this two locations, and the radius from R squared to this one. Okay. All right. So at least we see one property. Now you can see where it will go to a straight line. The circle will go to a straight line. And can you see that where what condition will make it go to a straight line? Instead of circle, it will go to a straight line. Yep. This is a circle, right? What condition of, from this expression, what's the condition that this will actually be a straight line? Oh, you can see, that's not, that doesn't work. It means the radius is 0. The radius is 0 means that point. This is a point. This is not a straight. You see that? So a circle, you can say that if you get the radius of a circle larger and larger and larger, that part of, at least part of the circle becomes straight. Any part of circle becomes straight line, right? Where what the condition? Yeah, this when the denominator is 0, right? So when R squared equals x0 squared equals y0 squared, that becomes a straight line. The circle becomes big, and then part of any part of it is a straight line. And to write down the straight line equation, obviously you can take the limit, but the easier way to do it is going back to here, because in this part we divided this factor throughout the whole equation, and that is not allowed if this is 0, right? When it is 0, then you don't divide it back. Just set the left-hand side equals 0. So this will be your equation. So for x squared plus y squared equals r squared, then the equation will be 1 minus 2x u plus v1 0 v equals that is the equation, right? And so now then we can go back to the last case. Using this formula to figure out the line, the equation for the line on the W plane. So on the Z plane, this is a circle that is going through the origin and one or I if you choose a complex number. And so the center obviously is 1/2. So for this case, so this means x0 is 0, right? This is a circle. So x squared plus y minus 1/2, right? So the y0 is 1/2. And the radius is also 1/2, so r is also 1/2, right? Okay. And you can see that obviously this would satisfy because x0 is 0, both y0 and r 1/2. So this satisfies this equation. And the reason is that this condition actually is just saying that the circle, the original circle, will hit the 0. Yeah. Which one?
The line.
What's this equation? This is just describing the shape. This one?
No.
This one? Where does it come from? This is for the condition when x0 squared plus y0 squared equal to r squared. Then in this step, we cannot divide it this. to the other side. This is 0. For this condition, this is 0. If the right-hand side is 0, the left-hand side is 0, right? Denominator is a finite, v squared plus v squared, but so the numerator is 0. But this is this equation. Okay, so that describes the equation for the straight line on the W plane. Because of it is they are linear. They're linear, so this describes a straight line, right? That is from just here, just here. You group these two together. That will cancel one factor of u squared plus v squared in the denominator. Becomes 1 over u squared plus v squared. So there's 2 give you 1. And the other two terms are this with this term, this with that term, right? The other is just move everything x0 squared and y0 squared to the other side. Okay. Okay. All right. Now we just plug in this equation. X0 squared is 0. Y0 squared is 1/2. So it's 1 plus 1 plus v equals to 0. But y0 is 1/2 or 1 plus. So v is minus 1. So it's so on W. So you get the figure in your textbook. So W prime. So -1 or minus I if you choose a compact number. So this is we know that it goes to here, but to figure out the sense of direction, you need to consider some limited case. So obviously, when you hit 0 on the z plane, this is a singularity, right? W is infinity because z is 0. So obviously, this will map to the infinity, both sides, right? And the top I will map to minus I. So this point will map to this point, whatever the text record. This is B. Whether this is B, it will map to this B on the W plane. So we know that this map to here, C will map to infinity. That now we just need one more case to know the direction. Say whatever. So you have positive. This will be 1/2, right? This will be 1/2, and 1/2 will map to what would that be? So basically, W will be 1/2 minus a plus I over 2. Yeah, there's 2, 1 plus I, 2, and 2, 1 minus I, and this is 2. The 1 minus I, this the minus I, y is minus I, is at a point 1. So this, whatever that calls, this called A in the text. This is called A. A will map to this one A. Right. This is right. 1 minus I. This 1 minus I is this point. So it means that start from B, move to A. Then on the W plane, start from B, move to A. And continue, you move to the origin, you continue, move to infinity. And obviously, when you keep moving or coming back from infinity, back to A, back to B. So the direction is like that. Right? Move around the circle. If you start from this point, go to infinity, coming back from negative infinity back to B. Right? That's the sense of how you transform it. Yeah. Well. Yeah. This one? This one? This one? Yeah.
I'm assuming you are using The y squared plus okay,
This one?
The top one.
This one?
Yes. Well, I'm asking how that you came about.
How you came? Okay, maybe I just skip. I just want to say some writing. So first, you do two things. So multiply u squared plus v squared to the left hand side, at the right hand side, and then divided this to the left hand side. This divided by here. So everything in the numerator divided by this one. Okay, and u squared plus v squared over there. And then I move the whole thing to the right hand side, but then I move everything back to the left hand side, change the negative sign. It's complicated, but anyway, after you move over there, you just let's consider the right hand side. You have a u square, right? After you move it back and divide that by u square, and everything you divided by this one. Now for this term, you have minus 2x your u divided by this factor, and then you move it back, move it to the right hand side. And that is this one. Okay, and that likewise, this one is this divided by that and move it to the other side. So you change the next one. Okay, and these two are just you add that, but you subtract it back from the other side. This is to do the complete square. I don't know. I do it maybe a little too fast. I assume you know how to do complete square. Usually, just look at the linear term. You figure out what I need to add. Must add the square term or positive term, so that these three terms will make the square. In this case, this one. So you figure out because you know the square formula, right? A plus b squared is a squared plus 2ab plus b squared. So you have a squared, and you from here you have a 2, and you have a, then this must be my b. You need to add b squared and subtract b squared. All right, that's how you do complete square. I'm just going too fast. I assume you can follow me. Sometimes it's maybe too fast for you, but because you're not doing my thinking. Sometimes I think by myself. I don't even you can follow. So yeah, stop me when you don't know what I'm doing. Okay, so but anyway, we figured out the shape. I mean the sense of direction of the mapping. Sometimes is important because once you know the sense of direction, you know roughly which point would go to this. So after you figured out, you know this point must go to somewhere here, right, and so on, right. And the last thing you want to figure out is which region will map to what region. So you like the interior of the circle now. Which region will we map to? Now the boundary is this straight line on the W plane. What region will the interior of the circle map to? We now see that. Anyone can see right away. Where will this interior map to? Anyone? Any suggestion? And for some reason, the bottom, why? Give me a simple reason.
We can take the circle like 5 and 2. That's going to be below.
Okay, yeah, that's a good reason. So choose a point and then will map to the region, and the region that contains that point will be the region that you transform to. So choose one point, and then you can see that you map to this point. All right, that's a good reason. Another way to think about it, you know that the lower part doesn't contain 0, the upper part contains 0. So when W is 0, Z is infinity. So the region that map to the upper region must contain infinity. So it must be the exterior. Exterior of Z equals to infinity. That will map to 0. Right? So another way to look at it. Yeah. This is just indicate a point. Just indicate a point. I just try to figure out what point this point will map to on the W plane. Yeah, you can choose any point on the circle that is convenient for you to map. Yeah, this means that this point on the Z plane will map to this point on the W plane. Well, any point is you can choose any point, but you determine the point that you map to by the relation, by the mapping. Okay. You choose a point here, use the mapping, and find out what the W value is on the W plane. Okay, and this is this is just an example. You just choose a point so that you can know the. Well, one point map to a one point, obviously. It's a map to what?
1/2, 1/2.
Is you choose a point that you find what point will point out. It's a continuous mapping, so it won't map to multiple points. This point only map to one point. Yeah, exactly. Yeah, because the function, this is a function, so a point will map to a distinct point. You don't map 2 points to the same at one point. Yeah, or 1 point map to 2 points. Yeah, you don't have the function is not multivariate. Yeah. Okay, and I think that's it for conformal method. Any questions up to here? So this is very simple, but some of the homework problem will be slightly more complicated, but it will be also more useful. Obviously, this is useful in some sense. Some application you might use that, but for more general application, you see use a slightly more complicated function, and some of the homework problem will have that. So, that's actually a group of transform that is commonly used as still not too general, but then it's much general, much more general than this one, and it can have it can transform to I mean, more complicated shape, like instead of circle, you try to map ellipse and things like that. Okay, so